Let's talk about a piece of math that, I promise, is way cooler than it sounds. We're not talking about some dry, dusty formula you have to memorize. Think of it more like a pattern-finding machine, a secret weapon that helps us predict all sorts of things, from a simple coin flip all the way to the chaos of the stock market. We're diving into the binomial theorem, and you're about to see just how intuitive it really is.
So to really get why this is such a powerful tool, let's start with a classic problem of prediction. It might feel like something straight out of a stats class, but trust me, it's the perfect key to unlock this whole idea.
Now, you could try to figure this out the hard way. You could literally sit there with a pen and paper and try to list every single possible outcome. You'd have heads, 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 tails, tails. Okay, that's one. Then heads, tails, heads, tails, heads. And as you can probably imagine, it would take forever, and you'd almost definitely miss one.
And yeah, it is a ton of work. There are 32 different combinations you'd have to map out, but what if there was a better way? A more, elegant shortcut that could just give us the answer without all that painful counting? Well, that's where our hero of the day comes in.
So, let's pull back the curtain on this elegant shortcut. We're going to unpack the binomial theorem itself and see how this ancient mathematical idea gives us a surprisingly modern solution.
At its heart, the binomial theorem is a formula for expanding something simple, like a plus b when it's raised to a power. But don't get hung up on the word formula. It's really a tool for spotting a beautiful, totally predictable pattern that's hiding inside these expressions.
And this is not some newfangled idea. The basic concept goes all the way back to ancient Greece with Euclid. Then, centuries later, minds like Blaise Pascal refined it, and eventually, the one and only Sir Isaac Newton took it to a whole other level. It just goes to show you how a simple idea can evolve over time to become a true cornerstone of math.
So, how does this shortcut actually work? Let's break it down piece by piece. Now, it might look a little intimidating at first glance, but I promise the pattern underneath it all is surprisingly simple.
Okay, here's the general formula. I know. It looks like a bit of alphabet soup. But just for a second, completely ignore those NCR things in the front. Just look at the A and the B. See the pattern? The power of A starts high and drops by 1 each time, while the power of B starts at 0 and climbs by 1 each time. Pretty straightforward, right?
All right, let's talk about those NCR things we just ignored. They're called the binomial coefficients, and they're basically the numbers you multiply each term by. Now, they look like the most complicated part of this whole deal, but there's an amazing visual trick to find them.
And here it is. They come from this beautiful thing called Pascal's triangle. Look how it works. Each number is just the sum of the two numbers right above it. And here's the magic part. Each row gives you the exact coefficients you need for a certain power. So if you're raising something to the power of 3, you just look at row 3. Boom, 1, 3, 3, 1. Power of 4, grab row 4, 1, 4, 6, 4, 1. It's just so cool.
So let's put it all together and see it in action. Let's say we want to expand x plus 2 cubed. First, we just identify our pieces. A is x, b is 2, and our power n is 3. Step 2, we go to Pascal's triangle, grab the numbers from row 3, that's 1, 3, 3, 1. Then we just combine everything, remembering our pattern of decreasing powers for x and increasing powers for 2. Do a little bit of simplifying, and there's our answer. No messy, repetitive multiplication needed.
Okay, expanding polynomials is a neat little math trick. But who cares, right? Why does any of this actually matter when you're not in a math class? Well, it turns out its applications are hiding pretty much everywhere.
Let's circle all the way back to our coin flip problem. The theorem is basically tailor-made for this. Why? Because those coefficients we found in Pascal's triangle, they aren't just random numbers. They literally tell you the number of ways each outcome can possibly happen. So the odds of getting exactly 3 heads isn't a guess. It's right there in the math.
Or think about finance. When you're trying to predict a stock price, you're not just guessing one number. It's really a tree of possibilities branching out into the future. The binomial theorem is the perfect tool to model that tree, to see all the potential outcomes, which lets analysts calculate risk and, hopefully, make much smarter decisions.
And what about something really tangible, like the bridges we drive over or the giant domes on stadiums? Engineers use complex polynomial expressions to figure out how stress and weight are distributed across those curves. And you guessed it, the binomial theorem helps them simplify and analyze those expressions to make absolutely sure those structures are safe.
And this isn't just old school stuff. In today's tech world, the theorem is a secret ingredient in making algorithms faster. In things like computer graphics or AI, sometimes you don't need a perfect answer. You just need a really good one fast. By using just the first few terms of a binomial expansion, you can get a great approximation while saving a massive amount of computing power. Now, everything we've looked at so far works like a charm for positive whole number powers. Like 2 or 3 or 20. But what happens if the power is something messy? What if it's a fraction or a negative number? Well, that's the very question Isaac Newton tackled. And his answer took this whole theorem to another dimension.
What Newton did was generalize the theorem into what's now called the binomial series. See, the classic theorem gives you a nice finite list of terms that eventually stops. But Newton's version works for any number you can think of as a power, like 1/2 if you want a square root, and the result is an infinite series, an expansion that just keeps on going forever. This was a monumental leap that opened up entirely new areas of math and physics.
And, this quote from Bright Champs really hits the nail on the head. At the end of the day, this theorem isn't just about getting an answer. It's a tool for thinking. It trains your brain to spot patterns, to think logically, and to take a big, complicated problem and break it down into simple, manageable steps. And those are skills that are useful absolutely everywhere.
So that leaves us with a pretty cool thought to chew on. The binomial theorem is, at its core, a shortcut for decoding one very specific, very important pattern. And it makes you wonder, doesn't it? What other incredibly complex patterns are all around us, just waiting for someone to find the right mathematical key, the right shortcut, to unlock a whole new understanding of our world?